Welcome to part two. This is organic chemistry, carbonyl compounds. So, this is the case of CBU, where organic chemistry is concerned. So we did the Greek and reagents. Now this is just part two of carbonyl compounds, and what are these? We'll be able to extract. So for more, you can join there. All right. So when we talk about carbonyl compounds, so when you talk about carbonyl compounds, all right, carbonyl compounds. So what are these? They are very simple actually. So provided we actually see what is happening with these, their reaction, stuff like that. All right, so carbonyl compounds, these are just compound containing carbon bonded to oxygen like that. Wherever you see carbon bonded to oxygen, you see we'll classify, I'll give some of the examples of carbonyl compounds. So they will change names according to what is actually derivated in them, like what is attached to them, to this, a functional group. Okay, so I said carbonyl compounds are compound containing oxygen bonded to carbon or carbon bonded to oxygen. So these, they are used as reagents. Okay, so they can be used as reagents. All right, used as reagents, and they can be they can be neutral or artificial. These, so the artificial ones we can talk of, like let's say plastics. All right, plastics are also made up of these carbonyl compounds. The other example I can talk about is drugs. Those drugs, they are made up of and artificial. So those ones which are artificial are the best example, these ones. Okay, then the other example that I can give is, let me talk about natural ones. Natural carbonyl compounds. Okay, natural ones. I've talked about the example of artificial. What about these? We can talk of proteins. All right. We can talk of carbohydrates. These are natural natural in nature. Okay. Okay. So that is it. So DNA. Okay. Nucleic acid in short. All right, nucleic acid, these are just neutral. Okay, so neutral and natural. So these are the best example of carbonyl. So I've defined the carbonyl compounds. What are these? These are compounds containing oxygen bonded to carbon like that, or carbon bonded to oxygen like that. These are what we call um, carbonyl compounds. All right, so now we have understood the the examples, and also we have defined these ones. So what are we going to do then? So let's talk about now the types. All right, the types that we can extract. The common type that we'll be studying under this topic here are what we call aldehydes and ketones. All right, so we said ketones, aldehydes are carbon bonded to oxygen like that compounds. So we can talk of now, like they are subdivided as ketone. Let me start with aldehyde. So aldehyde will see how the carbon oxygen is bonded and also what is in there. So it has also a carbon bonded to oxygen like that. Okay. Then at the end there, it's this carbon bonded oxygen is always at the end. That's one thing you need to know. All right. So then they can be a function of a chain of carbons, they are going down like that. So at the end there must be oxygen bonded to carbon, and that's all. That's what I need. Then the hydrogen, you know how to figure it out. So those are what we call ketones. All right. So aldehydes. So the other thing that I can talk about is a ketone. Okay. So what are these ketones? So ketones actually, they have this one, they start just with one carbon. Okay. But ketones, they have two carbons actually making that functional group. So if I talk about carbon bonded to oxygen, there must be other alleles, okay? Or the alkyls, the other carbons bonded aside, so for us to have this on the middle. So that's what we call a ketone. All right. So it possesses two carbon for each to start. Just like alkenes. Alkenes, Alkenes, they also have what? They have also the same thing, like they start at 2. Okay, that is it. So those are the things we'll be expecting. Now, um, if I'm to talk about, when we talk about the nomenclature later, I would have shown you how to name those compounds. So the case of ketone, the structure will look like this, where we have, let's say I can put, because of R, I'll make it like V-shaped like that. Because of carbons, which is, I mean, the oxygen which is rich in electrons, it will actually form the shape of water, which is bent. All right. So this is what we call a ketone. In short, for a ketone, for a ketone, we have um, for a ketone we have um, 2 oxygen at least. Then for aldehyde, we have the carbon bonded to oxygen, then the carbon is bonded just to one allyl or alkyl, then there must be hydrogen to balance the tetravalent of carbon. In short, the 4 bonds of what? Oxygen. You need to know how to figure out. You see a group, just know that whenever hydrogen is not showing, just know that it's showing, it's there. All right, so this is what we call an aldehyde. Okay, so know that this aldehyde will always be at the end. This functional group will always be at the end. This carbon will be the last carbon in that chain, whatever chain you have. Then the other thing that I can talk about, when we just have just this one, is what we call now, it can be bonded, it's waiting 2 bonds to be bonded. So together is called what we call a carbonyl. All right. So this is what I introduced, a carbonyl groups or carbonyl compound. This is the compound you've been looking, and the bond there is that what I've just listed there. All right. So from there, let me go you through with the classes of these. Um, okay. Let me create a space. Let me talk about the classes of carbonyls. All right. So classes of carbonyl. All right. So classes of carbonyl. Okay. So that is it. So let's talk about classes. So carbonyls, they are classified as one of ketone type. All right. So I think I have been repeating about ketones. So one, they can be of ketone type. All right, where we see R, okay, bonded to like the carbonyl bonds, I mean group, is bonded to 2 carbons like that. Then the other thing that I can talk of is the aldehyde. Aldehyde, you see it being bonded uh to only 1 carbon. Okay, the carbonyl group will be bonded to 1 carbon. I think you know that is hydrogen that is supposed to balance the tetravalent of oxygen. Then the other type of carbon I can talk about is what we call a carboxylic acid. Okay, so carboxylic acid also talk about, we'll talk about also the CO bond. That's what we are interested. So we see something like this where oxygen, I mean the carbon, is bonded like that. Then we have also the OH there. Okay, from condensation formation of this carboxylic acid. I mean, this is just how we can short a carboxylic acid. Then if they are to react with a base to form um, an ester. All right. So those are the things. This is how it looks. This is a carboxylic functional group. I'm sure you are aware of this. Then the other type of carbonyl group is I can give of ester. All right. So ester, the same thing, which is formed from esterification esters. So esters, if after performing a reaction of this carboxylic acid with alcohol, you form a functional group, something like um, the carbonyl that we are interested, then they must be also, they all bonded to a certain group, which is from alcohol. Is that clear? So in short, this is the here we couldn't have the R or the alkyl group bonded to that, but here under esters, is the hydrogen was removed there and replaced with this R there to form under esterification. This is the product, okay, ester. So that is it. So this is, we are only interested with the CO double bond. That's why I'm listing this. That's why it's called classes of carbonyl compounds. Okay, hope that make it clear. Then the other type I can talk of is um, acid chloride. We can have also acid bromide, acid. So we change just what is here. So if I'm to talk about acid bromide, you change, you put bromide there. Acid chloride, you put chlorine. Acid iodide, you put iodine there. So let me talk about acid chloride like that. So acid chloride, them they have chlorides, okay. They have the ara, okay, bonded to oxygen like that with that carbonyl functional group, then the chlorine there. So we have balanced the tetravalent of oxygen, and this is what we call, whenever you see like that, these iodide, the halogen groups, we call them acid halides, or you can say acid iodide if it was iodine here, acid bromine if it was bromine, acid stuff like that. They move like that, okay. Then the other last thing that I can give you um, is what we call the other type of the other type of carbonyl is what we call amides. So amides also, I remember we must see something, right, like a carbon bonded to oxygen like that. So we have carbon bonded to oxygen. Then there's this amide group which is Ni2 like that. So this is what we call carbonyl classes. Okay, all these are carbonyl classes. So hope that makes it clear. Let's go talk about the structure of this. So as you can see, let me talk about the structure. Okay, so structure of carbonyl compound. Let me just say structure. All right. So under structure, what we can see is that we have a carbon. Okay, we could see a double bond like that. This is not what happened in nature. Okay, this and the second bond, which you call it a pi bond. Okay, that is just a wave bond. Like it's not really guaranteed that it's there. No, it's not side to side. It's not flank to flank, it's sideways. All right. So the bond is just between there. That attraction that is felt between two atoms. They bond in that way, they bond in that way. Not really like bringing all the, because if you bring all the electrons under here, there will be repulsion here, and easily the bond can even like detach from each other and it can separate. You can't have a bond. That's how we just represent this bond so that you understand. Otherwise, that's not the case. So we represent bonds like that because the other bond is the pi. They are just wave-like. Okay. So I'll present it like this. Okay. Then there's what we call now the one I said these are wave-like. These are what we call. I've broken down that bond which was there, the arrow, the dash. So it is now the one in charge of these waves. Okay. Then remember, we could have something like, since it's like this now, we could have something like R there, all right, the alkyl group and also the R. You remember the structure that I drew for water, the case of ketone, all right. So the case of ketone, this is what we experience. And if you notice, let me just show you the bond angle here, all right. So if you notice here, there's that like 360 like that, okay, where we have 20, 120, 120 like that, okay. So this is also what happens. There's also 120 there, okay. There's also 120 there. There's also 120 there, and also 120. We have 120s, okay. So that's what happens. The bonds, these bonds are now the one in charge of, they are weak, the pi bonds. So something that has three steric effect or steric number is what we call a prana. Just prana. Prana, it is something that is prana, it is sp2 hybridized. Okay. It means that there are three groups bonded in that. So we can see three bonds. 1, 2, 3. That's why it's called sp, because 1, 2, 3 is giving 3. Okay. This is what we call sp2, which is a prana bond. All right, shape to say. All right, so that is it. Then coming to that, we can talk about let's talk about now like what really happens like for the bonds. Okay, the bonds of carbon and oxygen like that. This bond, um, the bond has the what I can say is, I want you to differentiate the two, or how this bond affect the other. So if I'm to talk about um, the bond that is between here, okay, and the bond that we can see, let's say in chloride like that, okay. Okay, I want to differentiate the two. You find that this bond it's long in length, because if suppose you are to break this one or to hammer it, it will go further than this can go. This maybe can go just like this. It ends there if you are to break them like that with a hammer. But this one is still like shrink, okay? So what I'm trying to demonstrate is that these pi bond they are very short, and for you to break this, you need a lot of energy. So need a lot of energy, need a lot energy, and also short length. Okay, allow me to write like that, short length. All right. So then these ones they are high length. All right. Then they have short, like the energy is small, need a lot, need small energy, need little energy, need less energy. Okay, so for you to break this, the reason is that this guy is more negative, right? And there's also another bond, so for you to break that, it's somehow challenging. All right, so that's the reason behind that, and you find that the bond length will be presented by angstrom. So just that for the CO4 chloride bond, we can find that it is somewhere 1.3, 1.8, somewhere 1.3 angstrom. It's not that important. I'm just showing you that these ones they will need, let's say, 1.23 the length. Okay, so it's not that long. So for the bond length to break the bond, you need a lot of energy for the two bonds there. Okay, so that is it. So this actually concludes to what we call the dipole moment exists in these two. All right. So the dipole moment exists in these bonds. So um, and I will demonstrate again the other bonds. I mean the dipole moment. So let's say dipole moment of ketones and aldehydes. So what are the dipole moments that can be experienced? When you say dipole moments, we're talking about between the two, which one has a good dipole moment, which one has a high dipole moment. We'll talk about that. So the reason is simple. Suppose the ketone is here, R there, and also bonded to R. Then we have oxygen there. All right. Then the case of aldehyde, no, this is, let me write this as which one should I call aldehyde? All right. Okay. Okay. Let me just talk about this. Okay. Okay. So if I'm to write like this, they have only one R there. Then there's also the H there. So this is an aldehyde, right? This is a ketone. Okay. So what will happen to the dipole moment? Which one has a large dipole moment? You find that um these are carbons, all right? So if you are like you are found with people who are rich, you find that you are also somehow rich in electrons. So these guys are rich in electrons, but this hydrogen only has one electron. So even if it's to actually disobey this family, the hydrogen will still suffer. Okay. So now what I'm trying to say is that the dipole moment of ketone, it will be quite high. Why? Because um, because these guys here, all right, the dipole moment we're talking about, the subtraction that exists between, if we are to find the electronic difference, electronegative difference. So what will happen is that um, and the ketone, this is a ketone, right? So the dipole moment that will be there is somehow closely to 2.9, if I'm not mistaken, dipole. So this means that for iodide is should be like dipole should be 2.7 dipole like that. So what is the communication there? The reason is that the dipole moment here is more. It's more like, let's say these are positive and positive. Together they are making positive 2. Then there it's just negative 1. Okay? Or maybe let's say it's yeah, negative 2. All right. Let me say negative 2 there. Then here we have only positive 1 and here negative 1. Let's say 1. Okay, let me just say negative there. Let me use signs. So here you find that adding these two signs, you get positive 2, right? Plus that one, you get positive. It will result there, okay? That's the reason why the dipole moment here, you find that this and this, they are cancelling. They are giving you a best resonance, which is reducing to 0. As you are intending to 0, the resonance actually become more stable. All right. So it's more like here, there are more electrons here, okay? There are more electrons to support this guy. Suppose this guy, this oxygen is to abandon the carbon here. Carbon will still get support from these rich guys. But here the carbon, it's giving 2 electrons, and if it's to break this bond, you find that there will be still a challenge there at actually arranging with. It has 2 pairs, okay? It contributed 2 pairs. Then here it's only finding 1 from this group. So you find that there will be that competition and the bond will reduce. Okay. In short, the bond will reduce. I want you to get this concept to say the more richer, the more the dipole moment. The more groups allowing the carbon, the more dipole moment. The less also the dipole moment. That's what the logic is there. I mean, that's the logic which is there. All right. As I'm concluding now, let me talk about now the resonance of this carbonyl. All right. Resonance. So resonance I talked on the previous one. It's about which one is more stable, preferably like with the one which we prefer the most to be used in organic reactions, stuff like that. So we'll be here to talk about that. Okay, that is it. So resonance of organic. So we are talking about an equal sharing of electrons. That's what we call resonance. So the resonance that is found in the alkyl group. Suppose we have H bonded to oxygen like that. Then how many? 2 have been used. So it means we have 2, 4, 6 there. Okay, 1, 2, 3, 4, 5, 6 to make 10. So this is there. Then it's bonded, let's say, to some alkyl group there. All right. So this resonance, okay, it is just like we can still like the resonance is about how we actually derivate the bond structure. So this bond, I can break it and this oxygen will get the negative, then this one will get the positive. So what I'm trying to say is if I'm to break this bond like that, this carbon is more, I mean, is an electrophile considered, which means it's more positively. Then there's a bond of oxygen, which is negative like that, okay? So this oxygen now, remember it had the electrons 1, 2, 3, 4, 5, 6. It has gotten those 2 electrons. Then this guy was bonded to 2 other groups like that. Okay, so which one is the best resonance? Resonance, we want like, we try by all means to get to 0. That would be the best resonance. So which one has a charge of 0? You definitely more like you choose this one than this because of the negative that you're able to see. You don't have to see a negative in that compound for you for it to be the best, because if it's like this, it means it's more reactive and you don't have to use it anyhow. It can react because it's less available for positive and negative charges. So this will be partial negative and this is, I mean, this will be partial positive, this will be partial negative when we break this bond, because this is more electronegativity. So that's what we mean. So this is the minor product. That's what we can say. Okay. Minor, this is the major product. Okay. So this, we prefer the major product, preferably. All right. So that is it. So that's what we talk about. That's what we mean when we say resonance. So you should change this. That's why I've been using this structure in all our reactions. Okay. Why? What could be the reason? The reason is simple. We are talking about polarization of carbonyl group contributing to the reactivity of the what? Of the ketones and electron. So you've seen this carbon, which is negatively, I mean positively charged, So under this is where we draw the picture to say carbonyl groups are led to react. Why? This one, which is considered when sometimes this carbon is positively charged, sometimes negatively charged when it is reacting with a metal. All right. So when the carbon is positively charged, it acts as electrophile, like it is loving electrons so that to cross that positive. So it's called electrophile. So when this carbon is negatively charged, um is called nucleophile. It means it's rich in electrons. So that's what we mean. This one is lacking. Um, when carbon is bonded is partial positive, it's lacking electrons. Partial negative, it has electrons that it can give. All right, so that's what we mean. So this marks the part one. Um, this marks the part one of carbonyl compounds. So thank you very much for your time. This has summarized your first, second lecture. Like these are lectures. So this is part one. So when I say this, I know what I'm talking about. Just follow this. They are very helpful. All right. Hope I've opened up your mind. Thank you very much.